In this video, we're going to be looking at the mechanical applications of vectors and vector addition. What we're going to do, we're going to explain the differences between distance and displacement and position. We're also going to apply vectors in terms of adding and subtracting them to different applications, such as finding a position of an object, a resultant or relative velocity, net torque, or force. This is stuff we're going to be doing throughout the entire year. So as you're watching the video, if you become a little overwhelmed, that's totally all right. We're just looking at the different applications. If you can just see how we're adding the vectors to not truly understand the full context of the situation, that's what we want you to be right now. We just want you to understand how to add and subtract vectors and to realize that they're going to be used for a variety of different applications. Why are we doing this? Because even though vector applications is very diverse, the methods that we do to work the vectors is always the same. It's basically just adding and subtracting. Becoming more comfortable and proficient with these skills takes a lot of practice, and this understanding takes exposure and time to do so. So we're starting it now, and you're going to see all the different applications in the beginning, and then we're going to just progressively work you through them throughout the year so that as you need these skills, you'll be very proficient with them. So here we have a person that's running around a quarter-mile track. It's your typical track for that you would find at a track and field event. And the question is, do they go anywhere? Now, there are always two great debates on this. If you have a distance perspective, often runners have this type of perspective. They say, yes, you've traveled a quarter mile, you've run the 4 laps, you've done the mile. And it's not about that you end where you started, it's about the journey in between. That's the runner perspective. So it's very easy to say that the runner did, in fact, run somewhere. However, if you're more like my wife, who doesn't like watching track because they start in one spot, they run in a circle and end where they finish, she has what's called a displacement perspective. You could have just stood there for the same amount of time and got into the same position in the end. Displacement is not position. Displacement is a change in position. Distance is a vector value. I run 5 miles. It could be north, south, east, west. It doesn't make a difference. Displacements, however, though, will have a distance. How far am I from where I started? And a direction. So if I started at a location, I ran 1 mile east versus 1 mile west, the distance just tells me I ran a mile. Displacement, though, tells me that I'm in 2 opposite ends because I'd be 1 mile to the east or 1 mile to the west from where I started. We often can describe position a couple of different ways. You always have to pick the perspective that's most applicable and most convenient for what you're trying to do. One of the classic ways that we'll view things is through a translational or tangential position. These are just everyday distances, in all honesty. So I have my quarter-mile track here, and I'm running around, and you can see the distances that the person travels. 50 yards, 100 yards, 300 yards, all the way back to 400 yards up over there. However, if I'm looking from a person's point of view from standing in the middle of the track, they see a person standing at, let's say, this top position, and then they end up in this position over here. If I had another person standing up over here running this way, they would not have run the same distance. The person on the outside runs a longer distance. That's why if you watch track and field, the tracks actually for a quarter-mile race actually have different starting points. The person on the outside starts much further ahead than everyone else because they have a much longer distance to travel. So that makes the race more fair. But the angle at which this person travels from here to here, if I'm just to rotate my position, is exactly the same. So you can think of this as a person looking forward, and the question is, how far do I have to tilt my head to watch you travel? So if I look at it from an angular perspective, this guy has traveled an angle of 90 degrees. This guy over here traveled a distance of 180 degrees to 70 degrees. So we can often look at things from an angle perspective. Which point of view is better, the distance or the angle? That all depends on what you're trying to do. If I'm trying to figure out how far I have to travel, how much fuel I need to complete the loop, I would want to use a tangential perspective. If I'm just trying to set up a camera to track how this person is going to run, I'd probably want to use an angular position point of view because the angle is going to simply rotate to follow the person. The link between tangential and angular has always been through circumference. Most people know the equation circumference equals 2 pi r. The 2 pi isn't just a number, it's the actual angle around a circle. 2 pi is actually 2 pi radians. It's a unique unit that we use that relates the radius of an arc to the tangential distance across the arc. For us, 1 radian is always equal to, pi radians is always equal to 3.14, and pi radians, 3.14 radians, is actually equal to 180 degrees. So a full circle, 360 degrees, would be 2 pi. So that's where this comes in. Circumference is really, instead of 2 pi r, 6.28 radians times r. If I'm working with just a fraction of the circle, I'm going to work with just a fraction of the 2 pi. That's just going to be my angle. So a lot of times some of you guys might have seen this equation in the past. Arc distance is equal to theta r, where theta is the angle that you have for the two arcs, the angle to complete your arc. But it really is just a fraction of 2 pi for the complete circle. So this here is a base equation. You get this constantly. You do not need to have it memorized. You just have to be comfortable enough to use it. Now, we're not going to use it a lot right now, so if you're not comfortable with it, that's okay. If you've seen this, go, I kind of know this, you're ahead of the game. When we're dealing with translational directions and positions, we'll often be working with positive and negatives. The positive x, the positive y, negative x, negative y are all very intuitive. And if we look at the north, south, east, west perspectives, it's very much like an xy axis. So we often pick east to be positive, west to be negative, north to be positive, south to be negative when we're dealing with our vectors. For our angles, there's only two directions, clockwise and counterclockwise. So anything that rotates clockwise will be negative. Anything that rotates counterclockwise will be positive. The reason for that is if you take a look at the way that we often first viewed angles with you guys, they're measured from the x-axis. So if I'm going above the x-axis, that was a positive angle, and that's in the counterclockwise direction. However, if I'm viewing an angle that's going below the going below the positive x-axis, we said that was a negative angle. Well, that's actually a clockwise rotation. So we're just expanding now this positive angle to a complete circle. So counterclockwise is positive, clockwise is negative. Here's a fairly involved set of questions where if a person's going to run along a circular track, the radius of the track is 140 meters. Their starting position is 2 pi radians from some arbitrary reference that we're using, and they're going to run 6 pi radians clockwise. And then they're going to run 1.5 radians counterclockwise. And I want to find out the angular distance that they ran, the tangential distance they ran, their angular and tangential displacements. And I'm not going to lie, first time out, this sounds very overwhelming. However, we can take this piece by piece. Distance, that's just how far I've traveled. So I'm going to look at my radians simply because I'm looking at my angular distance. So the guy ran 6 pi, then they ran 1.5 pi. So in the end, that's 7.5 pi's that they ran. What about their starting position? That has nothing to do with how far they traveled. That's just their arbitrary starting point. I need to know that for where do they end up, but not how far have they traveled. To find their tangential distance, I'm going to just use the equation S equals theta r. That's it. Theta is 7 pi radians. My radius, 140 meters. I'm going to just simply multiply that through. But instead of working with pi, 3.14. Keep everything really simple with this. Mathematics teachers, they will love you to keep things in pi because pi is not a rational number. And so if you have 7.5, it is far more accurate than whatever 7.5 times 3.14 is. However, while that's philosophically true in terms of practical application, it's not important to be that accurate. So 3.14 is accurate enough for us. I now want to find their angular displacement that the person ran. So I have to consider their directions. So the person first ran 6 radians clockwise, which is negative 6, sorry, they ran 6 pi radians clockwise, so that was negative 6 pi radians. And then after that, they ran 1.5 pi radians counterclockwise, which would be positive 1.5 radians. So if I go negative 6 pi, then I go positive 1.5 pi, that's going to be added up to negative 4.5 radians. So the distance, the magnitude aspect of my displacement is 4.5 radians. Since it's negative, the direction is clockwise. So my displacement is 4.5 pi radians clockwise. How do I find my tangential displacement? I'm still going to use the exact same equation that I did before. S equals change in angle R. But this time, change in angle is 4.5. So 4.5 times 3.14 times 140 gives me 1,978.2. This is a negative number because I ran clockwise. So my displacement has both magnitude and direction. So 1,978.2 meters clockwise. Had my answer been positive, it would have been counterclockwise. These are far more intuitive for us. We think much better in terms of north, south, east, west than we do in terms of angles. A person runs 400 meters west, then 300 meters east. What's the distance they travel? What is their displacement? Distance traveled is very intuitive. I ran 400, I ran 300, that's a 700 total. To do the displacement, I actually have to add up my vectors. So I draw out a vector that is going to be for 400 meters. I'm using a scale of 1 centimeter equals 100 meters, so that's 4 centimeters long, going in the west direction. At the tip of that vector, I draw a second vector. I have my origin. It is going to be on the same scale, so it's going to be 3 centimeters long, and then from start to finish, I'm going to draw my resultant. That's the one in red. I measure it out, and lo and behold, it is 1 centimeter long, which means I have a displacement of 100 meters. The arrow points to the west, so it's 100 meters to the west. I have a person who now runs 400 meters west, and then they run 300 meters north. I want to find the distance that they travel and their displacement. The distance they travel is still 700. I ran 400, I ran 300. Distance has nothing to do with the directions that I'm going in. My displacement, though, will be very different. I'm going to run 400 meters to the west, so I draw my vector exactly like I did before, and again it is 4 centimeters long because I'm using the same scale. Now my new vector goes straight up. I have my origin, I draw in the north direction, and 3 centimeters long. I now have to draw from start to finish. I have to now measure out my angle. And I have to measure out my magnitude. My angle comes out to be about 35 degrees going above the west direction. So that's 35 degrees north of west. If I had preferred, I could have used 145 degrees, but that's going above the east end, which is a little less intuitive for people. But if I'm going east, this would be all the way around here. So that is going in the north direction originally. So going north 145 degrees. I could also have measured my protractor along the north-south-east axis if I wanted to. And I could have measured at 55 degrees west of north which would be starting from the north, going 55 degrees to the west, or west of south, going this way, 125 degrees. I never have to give all four. I just have to give one. So I pick the one that makes the most amount of sense for me. I can measure the hypotenuse length. That's 5 centimeters, so it's 500 meters. Some people might recognize this as a 3, 4, 5 triangle. So I can now turn around and give my answer. And please notice I'm using the word or. I don't have to give both of these answers. I can give only one. I give the one that makes the most amount of sense to me. So I can say it's 500 meters at 35 degrees north of east, or going north from the east, or 500 meters at 45 degrees north of west, which means going north from, 500 meters at 140 degrees north of east, which means I'm going 145 degrees going north from the east. One of the things we're going to look at throughout the year is something called torques. Torques actually are very easy to add by doing vectors because just like angles, they only have two directions, clockwise or counterclockwise. So here I have a wheel that's being twisted by 3 torques. They are 400 Newton meters going clockwise, 200 Newton meters clockwise, and 900 Newton meters going counterclockwise. And I want to find the net resultant torque. Now, one of the things that people might get confused with right away was what on earth is a meter Newton? And the truth is, right now, I don't care. I've got 3 torques that are being added up, so I'm going to just add them up like vectors. It's like if I was being asked for what's 4 widgets plus 8 widgets. I don't know what 4 widgets plus 8 widgets are because I don't know what a widget is. Yes, I do. Okay, I can still answer it. 4 plus 8 is 12. I'm just adding. I don't care what I'm adding. So I'm going to just simply either draw these out, which becomes very convoluted, I am not going to lie, or I can just use plus and minuses. So anytime I do anything with an angle or a torque, I work with plus and minuses. So 400 clockwise is negative 400, 200 clockwise is negative 200, and 900 counterclockwise is positive 900. So I have negative 400 plus negative 200 plus positive 900. That's positive 300. So positive means counterclockwise. So my answer is 300 meter newtons counterclockwise. Again, not really talking about what a meter newton is. Don't really care at this time. So we're just adding up our vectors. All right. Here I have a disc that experiences 3 different torques of 100 newton meters going clockwise, 800 meter newtons going counterclockwise, and an unknown torque. The net resultant torque, which is the sum of all of them, is 50 meter newtons clockwise. I want to find the unknown vector. Well, in this particular case, I can set up like an algebraic equation. My summation is equal to all of my vectors being added up. So my unknown vector is really my sum minus the 2 individual vectors. So I'm going to now have to subtract vectors. But subtraction is really adding the opposite. So instead of going 50 meter newtons minus 100 clockwise, I'll say 50 meter newtons plus 100 counterclockwise. And then instead of subtracting out 800 counterclockwise, I'm going to just add 800 clockwise. Now simply add these up, and I come up with a negative 750 meter newtons, which is 750 newtons clockwise. One of the ultimate classic ones that you'll see is when we have multiple forces acting on an object and the net force is going to be 0. So we're going to solve this the exact same way we did before. I'm going to actually set up an equation for each one of my forces, adding them up, setting them equal to 0, and then I can solve for the unknown force. So my unknown force is equal to 0 minus all of my forces. So I'm going to just simply add the negatives of each of my forces together to find the resultant. And that resultant is, in fact, my unknown force. All right. Well, I hope this makes a little bit of sense. Like I said, We will go over this in greater detail a little bit later on, and I will see you guys in class.